At the Big Bang, scientists believed that the universe was rich in pairs of matter and antimatter. For those who don't know what antimatter is, antimatter would be a mirror image of matter. It would have the same mass but opposite electric charge. This means that in antimatter, we have antiprotons with a negative charge, unlike protons, which have a positive charge, and positrons, also known as anti-electrons, with a positive charge, unlike electrons, which normally have negative charges. Very well. A very interesting property of antimatter is that if matter and antimatter come into contact, they would annihilate, leaving only energy behind. In theory, this would mean that in the universe, there should be nothing but energy. Because if the same amount of matter and antimatter were created, and they annihilate upon contact, you would have only energy. However, there is a great mystery here, where at some point in the universe something happened that broke this symmetry. And what we see here, basically, is only matter. Could it be that we live in a pocket of matter and there's a pocket of antimatter elsewhere? How does that work? We don't know. In the universe, we know the places where antimatter is generated. We have satellites that have already detected the creation of antimatter. For example, collisions of cosmic rays with the atmosphere create antimatter. So what's the issue? The issue is that antimatter is quickly annihilated when it encounters matter. So, there's no problem. That's what happens. Another place that generates antimatter, which scientists have discovered, is those relativistic jets from black holes. In other words, high-energy phenomena in the universe typically generate antimatter, gamma-ray bursts, and so on. And a very interesting property of antimatter is its potential for antigravity. It indeed has this property, but it would need to be experimentally verified because if antigravity exists, it would contradict Einstein's general theory of relativity. Why? Because in the general theory of relativity, Einstein predicts that all masses, regardless of the differences in their internal structures, react in the same way to gravity. That's written in Albert Einstein's general theory of relativity. So here's the big question for scientists. How do you test if this hypothesis is true or not? There's only one place on Earth where we know this can happen, and that's the CERN. At the Large Hadron Collider, LHC, at CERN, you have this possibility. In other words, there's an experiment there called Alpha where this test could be done. So that's what scientists did. They went to CERN, and the first thing they did was create antimatter, which is antihydrogen, composed of an antiproton and a positron, to conduct the test. Very well, the scientists took the antihydrogen particles, kept them in a magnetic bottle with a magnetic field they could control. So there was a bottle, there was antimatter, and they could control this magnetic field. These magnetic fields were reduced so that the particles could start moving around inside the magnetic bottle. You understand? And what did the experiment show? Well, if anti-gravity were valid, the particles should have risen. But what happened was that 80% of the particles drifted to the bottom of the magnetic bottle. Furthermore, the researchers repeated this experiment dozens of times, and in the dozens of times they repeated it, the same thing happened. What does this mean? It means that the conclusion of the experiment is that gravity, which pulls things down, right? You release something here, and it falls. Gravity also acts in the same way on antimatter because it acted in the same way on the antihydrogen particles, pulling them downward. Moreover, the scientists were able to measure the gravitational acceleration of antihydrogen and concluded that it's very close to the acceleration of gravity in normal matter, which is 9.8 meters per second squared. In addition to demonstrating that anti-gravity doesn't exist, all this experiment conducted by the researchers at CERN showed what? That Albert Einstein was right once again, meaning that once again, another prediction made by his general theory of relativity worked perfectly. This demonstrates how robust Albert Einstein's general theory of relativity is, as it's tested, retested, tested again, tested in different situations, and it always holds. This is very interesting. So, if this happened, does it mean it's over? Does it mean it's settled? No, it means it opens up the opportunity for new research related to the gravitational nature of antimatter. Because antimatter, which is supposed to be matter's mirror image, behaves the same way when it comes to gravity. So now, researchers will put efforts into trying to understand the gravitational nature of antimatter. So there's a very interesting study. The article was published in Nature. And it's another breakthrough in science this year, showing that Einstein was right, and that antimatter also experiences the same effects of gravity as matter, proving that Einstein was correct, proving that everything is working as it should. Folks, this was the video I wanted to bring to the channel for you today. I hope you enjoyed it. If you did, you know the drill. Don't forget the YouTube Bistic package. Share, favorite, subscribe to the channel if you're not already. And leave your comments on what you want to know. And if you want to learn about more amazing discoveries, watch some of these videos here. Until next time.